All right, welcome to today's session. Uh, I'm bringing a new innovative way on how we can be able to encrypt sound. We always know in the process of transmitting sound, hackers can be able to get through it, or else maybe the particular information can end up landing onto the wrong source. So for clarity, I have a problem, I have a challenge here that I'm trying to solve. We have one phone at home, it's a father's phone. And that father has a very beautiful queen, a very beautiful daughter. And here is some high-tech guy at a distance who wants to get in touch with this lady and talk to her and find out what her opinion is. But he has to use the same phone, and he decides to record his audio. He knows that he has trained his girlfriend, his precious queen, on ways that she can be able to decrypt this sound and maybe play it in its readable, in its much more clear form. So this is the point. Here in this case, I'm going to take you through a systematic step-by-step process. I've recorded some dummy sound, just A, B, C, D, E, F. Of course, later that sound can mean anything that we can use for the whole process of encryption and see how that sound eventually gets distorted. So particularly, I'll begin with importing my libraries. For those who for just clarity, I'm using Python and I'm here using an Anaconda distribution, specifically Jupyter Notebook. So I want to see how to import my libraries, which libraries I'll use in this particular process. So first of all, if those ones who do not have some of these libraries, you can be able to install them. But let me start by importing from scientific Python, scipython.io. I want to import this particular sound format. The sound format is a WAV file format, so I'll call it WAV, WAV file. And in that case, I'll also import NumPy as NP. I'll import NumPy as NP because I don't want to keep writing NumPy as NumPy. And then on the other side, I'm also going to display my sound in form of maybe a graphic kind of importations. I'll import matplotlib and matplotlib.pyplot and take it as just PLT. And then I'll also import my sound device because I want it to be able to hear my sound and translate it. So I want to take it as a sound SD. If you don't have this particular sound device, you can be able to install it. And for me, I have it. So for you to be able to install it, you can use the pip install command. And then you put sound device. And when you run that, if you don't have it, you'll definitely install. Remember, you must have internet to do that. For my case, it's already satisfied because I have it. So that's great. So then the other thing, I'm going to take this sound as some frequency. And I want to assign it a name data. And it's a web format, web file type .read. I want to pick a particular extension where I've saved it in my computer. So in this case, I've saved it in that particular extension, my computer. So that's where I'm picking it from. So I want to plot this, and the best way on how to plot it, I'll plot it in some bit of a graphical image so that I can be able to see how that sound is moving, how its movement is, how its frequency is. Maybe just for smoothness in my graph, I will give my graph a title. So let me call that title original audio recording. And then I will want as well to be able to have the different frequencies outputted as some numerical kind of data so that we can be able to plot it. So I'll reassign some new thing. I can call it data1. And I'll say, let it be outputted as a numerical array, And what is it picking? It's picking my data. And I would want to call its data type to be a numerical integer data type. So I can take off 32 bits. You can play with that as much as we want. So let me run this. If I see this is how my audio is displayed, this is how it's moving. This is the A, B, C, D, E, F, and so on. So we could even play this so that we can see how what kind of sound we have. So I'll still use that sound device that I installed, so sd.play, and then I'll pick my data as a frequency data set. A, B, C, D, E, F. So that's how our data set plays. I can replay this again so that we can be able to see how it is. Great. So that is the data that we're going to encrypt. And since it's the data that I'm going to encrypt, I want to use a particular encryption algorithm. It's called the RSA. RSA comes from three inventors, Reverse Shamir and is it Ahmad, something like that. Read more about it. And specifically, this algorithm takes me through three steps. One step is the public and private key generation. Maybe just for clarity, it's an asymmetric encryption algorithm where two keys are required for encryption and decryption. So in this case, we have a public key, and then we have a private key. So meaning I'll give the other lady maybe a private key for her to be able to decrypt this message, and then I'll be able to use a certain public key for encrypting this message. So if that's the case, I'm just going to paste this here, and I'm going to take this as a markdown because I don't want it to compile it as code. I just want it to display like that. Then this goes back to code. So what I'm going to follow these steps. We can change this for as much as we want. Maybe I could take any other prime numbers, pick any two prime numbers of choice. I'll pick 53 and 59. And then to generate my public key variable n, I'm going to multiply p and q. And then as well, I'll pick an integer value. And that integer value, I'm going to make sure that that integer value that I'm picking is not a factor of n. And as well, that value e is going to be in between 1 and the quotient n. And we shall discuss a quotient much more in details. So I've decided to consider my e to be 3. And if that is the case, I'll generate my public key that will be generated will be n and e. So if that's true, I'll go ahead to calculate my qn. And the expression that I'm going to use for calculating my qn will be p minus 1 and then q minus 1, whereby my qn in this particular case will be 3016. And finally, I'll calculate my private key d, where my private key d is going to be a fraction of k times qn plus 1 divided by e. Remember, we'll have gotten the value of e, would have assigned it to something, and the value of k will take on values from 1 up to a certain value n, integer value. So in this particular case, I want to pick an integer value of 2, and meaning if I substitute, my value of d will be 2011. So if that's okay, let me start my process. Instead of using p and q, I want to take p1. In this particular case, I want to prompt my compiler to input some two prime numbers. I'll give a space for entry, and then I want it also to enter another second prime number, which is also an integer value. Let it input another second prime number, which is also going to be of that nature. And if that is true, I'll calculate my value n, which will be p1 times p2. And finally, I'll ask my compiler to print for me that value n, which is the same as p1 times p2. And this should be equals to, I'll give some space, and all that should be the value of n. So let me enter this. The first prime number that we took was 53, and the second prime number is 59, and it gives me my 3127. So the next step is for me to calculate my e and k. I will also ask my compiler to just allow me enter some two values of e, which is an input value. So I'm asking you that please enter a small odd number, which is a core prime number with n. So let it enter that. And then as well, I'll ask it to be able to allow me enter some integer value k. So it's an integer value. Just allow me to input it. So I'm instructing it that please enter a value of k. So if that is done, I can run this. Let me enter my co-prime numbers 2 and also enter my value of k as 2. And finally, my phi n is what I want to calculate, this expression here. So phi, my compiler understands as phi into the value of p1 minus 1, even though it's space, it's fine, times my p2 minus 1. And if that's the case, I'll ask you to print for me that value of phi, but it's case sensitive, which will be equals to, and then comma, let the value be the phi value. And if that's true, let me put now my value of d. I want to have this formula that we disclosed here to be able to be captured. So that formula, that value of d, it's an integer value. You can declare it as a floating value. So it's okay. So I'll take it k times phi plus 1. And the whole result is going to be divided by e. And if that is true, then I'll print my value of d, which is equals to my value of d. Let me check that. And I compile that, it picks my value of phi and picks my value of d. They are all the same values. You can try and enter the value of phi, which you got up here, enter the value of k, which is 2, and divide by the value of e that you are pre-calculated somewhere. The one that you got from here, you entered it here to be 2. So if that's the case, my private and public keys for encryption, I want to call it private key. Now it will take on two values n and e, and also my public key will take on two values n and d. So if that is the case, I will want it to print for me my private key. I will just copy this just for fear of making mistakes by humans, to be equals to, and then let it display for me that private key. I'll also copy this public key, and I'll also want to print it. Print my public key. So in this case, this is my public key, and I would want it to display that public key. So let's check. Now it has picked the value of the private key to be the n value that we got. Where was our n? Our n was here, 3127, and then it has picked my value of e. My e value is what I captured here as 2, and we can see that's what is displayed here. And then my n still, which is 3127, and my d value, which I got here to be 3016. So this is what I'm going to use. I've finished to build my algorithm. This is my RSA algorithm that's going to help me do the encryption and decryption of this particular sound. I want to see how the sound is going to be distorted from the original sound. Let me replay my sound. So that's the sound we have. So that's the sound I want to encrypt so that we can be able to see how the final output of my sound will be. So this is where now my real encryption process begins. So I want to take this as a markdown, and I'll run this. So I'm going to encrypt the encrypted value, maybe just for clarity purposes. My value that I'm going to pick the message itself, which in this case the sound, which sound I decided to call my data here. I'm going to pick this data, put the power of e to it, and then get the modulus of that whole result with n. So it is data to power e mod n. So for me to write that, I'll put it as data to power use those two values e, and then modulus I'll use my percentage n. And because of that, I'll plot, because what can make me best to see my output is a graphical representation. I'll plot it, and I'll put a title on my graph. I'll put a title on my graph, and my title is going to be my encrypted encrypted secret audio. Good. So if that's the case, let's display this and we see how it's going to look like. And that's where we can actually be able to, that's where we can be able to, where we can be able to, how we can be able to view our audio. I'll see you the difference. I'll see you the difference. I'll show you the difference so that we all view and see how different our respective audio would be. So okay, so let's just compare. Let's just compare. This is the original sound, and if we look at the original sound, this is the distorted sound, and this sound has been changed. If you look at the frequency, how the frequency was from here. If we look at how the frequency was here, and we compare it with how the frequency is here, we can actually be able to see a lot much more difference in related to what we are doing. So that's great. So maybe the next case, I want us to see how we can be able to download this sound and be able to play it, and maybe later be able to transmit this sound to its intended person. So for us to be able to save the sound, I'll still go back here, and I'll want to save this sound. And for me to save this sound, I'll still use my encrypted data assigned, and I'm picking it as an array. And what's going to happen? It's an encrypted data type, which is a numerical value of 16 bytes. What I've done, the original sound had 32. I've decided to have that because I want to change its quality. Let me take you to why I had that 32. It's here. I want to change its quality from 32 to 16 so that the final meaning is completely distorted, so that nobody can be able to understand what my file is. So still, I'll want to write it as a web file so that I can be able to still listen at it, and I'm branding it as encrypted sound to maybe charity. So this is a sound charity, maybe through the father's phone, or through maybe the father. Let me call Adrico, my girl Adrico, encrypted sound to charity through Adrico's phone. So this is what I have, and this is what I'm going to transmit. And I would want to print this as a file titled encrypted sound. Maybe this may be to, let me copy this, I'll put it somewhere. Let me just have a short name that I can easily be able to pick. I'll just display that somewhere. Let me write this encrypted.web. It's a web file, and how I'm treating it, I want it to be a frequency and as well to remain encrypted. And then this is the title of a file type titled that, because it's titled that. Where am I transmitting to? No, the first title is encrypted.web. That is the first title, and that sound is going to be generated and saved in, sent to that phone. Let me play this. It's picking some syntax error, and the syntax error, it's picking it from this double quotation. So maybe let me use a single quotation here, and also use a single quotation here, so that it differentiates. So this has run. Now that it has run, I could be interested at loading this sound so that we can actually be able to view it. I want to load and decrypt my sound. I want to load and decrypt my sound. So what I'll do, I'll click on this, and I just want this to be text without compiling. That's why I press that. So it's going to be my frequency, and maybe I want to change its name now to be data, and this is going to be equals to wave file dot read. I want it to read for me that encrypted file, and its name that I chose to put was encrypted dot wave. And I wanted to plot this graph so that I compare it with what we encrypted. And I'm plotting that new data file. Remember, I've changed the name from the small d to now capital D as data. Then I'll do my plt.title, and it's encrypted audio to charity through Adrico's phone. And when I run this, that audio now shows, and we can see this is the message. This is what is going to be downloaded. So it's the same. What has been sent encrypted and what will be downloaded on the other side will be the same. And I could be interested now to see how my decrypted data will be. How is it going to be? And let me put it as a markdown and I run this. So my decrypted sound, what I'm going to decrypt, that will be distorted, is going to be the data itself that we picked to power D modulus N. So D and N, remember from here, in this case it was E and N used, meaning this is where the private key was used. And then the decryption process now required the public key D and N. So that's where I'm now using my public key, which public key is known to Charity. So meaning the person who is sending it will communicate to Charity a private key before, so that she decrypts this appropriate message. And in this case, my plt.plot will be decrypted message. I want it to plot for me that decrypted message. And it just picked it as this. So let me remove this and put these brackets. Good. And then my plt.title, I could now call this decrypted message. What name can I give it? I can just give it that click and win. And this is what Adrico will see. Adrico will be excited. And maybe when he clicks and he sees some distorted sound, which is this sound that we're viewing, which sound we could play. Let's see what he'll play. If I put .play, then I put encrypted as a frequency sound. So when he sees the message click and wave.wave, he'll play on it, and that's what he hears. So when he hears that kind of encryption, let's check. The original message had a particular sound, and this is the sound that the original message had. And this is what the encrypted message will be that will be decrypted on the phone. So it means on the other side now, this decrypted message can then be replayed, maybe converted back into its original shape, so that it will be used for an appropriate work, meaning the person who will download it or share it on the other side will be able to understand what specifics her message has. So I think this is the end of this project. It's a good project, and it's a good project in security. Thank you.